Hello, so welcome to this video. So in this video we're going to be looking at density matrices and their use to describe quantum mechanical systems made up of different parts. Now this video is here because there's been a few videos on state vectors which are used to describe systems we consider as a whole in quantum mechanics, where we're not concerned with subsystems. However, for topics like entanglement, where say we've got two particles, we can think of each particle as an individual system, if you like, and therefore, when looking at entanglement, we can think of the two particles together forming a composite system, and therefore we describe the state using density matrices. And since entanglement is a very interesting topic that I know lots of people find fascinating, and it does have many fascinating properties, and it also comes up a lot in nature, it is worth talking about why we use density matrices to describe composite systems, and this will also be a good introduction for those which might be unfamiliar with this way of thinking about the state of a system or a composite system, and therefore will help anyone that is looking into the mathematics of entanglement or wants to understand more of the technical details. But density matrices is one place where matrices appear in quantum mechanics, but it's also worth initially going through other cases where we see matrices in quantum mechanics. And so this video would also act to show why matrices are useful, although we will culminate in a discussion of density matrices. So that's kind of this video, and also in this video, whilst there will be a bit of maths, I'll be mainly talking about how it works in a kind of descriptive sense with a lovely picture to show an equation towards the end, which will help us understand why we use density matrices. So there is going to be a bit of maths, but this isn't too heavily mathematical. So I'm going to go through this fairly quickly because I have other videos talking about states in quantum mechanics and how we describe the state of a system using state vectors. For those that are unfamiliar, I'll summarise it here, but if you would like a bit more detail, I would recommend my video on the hypothetical experiment of detecting a bomb, which is a thought experiment which discusses a very strange feature of quantum mechanics called information-free measurements. And that's a video that I'll link down below this one. But anyway, it's worth summarising what states are and how we describe them in quantum mechanics. So the general idea of a state in physics is a description of something that captures something about a physical measurable quantity of the thing in question. So for example, if we've got a mug of coffee, part of the state of that system might be the temperature of the coffee. It could also be the volume of coffee in the mug. It could be the size of the mug. All these things could be states. Equally, if we're interested in a very comprehensive description of the mug and the coffee, we might need lots of pieces of information to talk about the overall state of the mug of coffee. Although generally in physics, because we're only trying to measure one variable at a time to make our lives easy, when we talk about the states of a system, we really mean the value that system or object has for a particular measurable property. So it could be mass, it could be colour, it could be many things. And in quantum mechanics, because in quantum mechanics the state of the system, when observed, can actually lie between classical states. The state is kind of like an arrow which can move towards or away from one classical state to another, and when observation happens, the arrow flips almost instantaneously, if not instantaneously, to pointing along a particular classical state. So because of that, it's natural to think about a quantum state as a vector with components, with the components corresponding to how much of that vector is in each of the possible classical states. So we would represent the state of a quantum system traditionally using a vector or a state vector. And this immediately brings us to our first application of matrices in quantum mechanics. Because we know that from linear algebra, a matrix can turn one vector into another. For example, rotation matrices can rotate one vector into another vector, and we have a diagram in the blue box showing this, where we have a vector being rotated by an angle theta, and the rotation is caused by a matrix which I've written for a summary below, although it's not too important, but it's there for completeness. So matrices can change one vector into another. And therefore a matrix can cause a vector, if you like, to evolve. And because vectors represent states of quantum systems and quantum mechanics, this means a matrix can describe the evolution or the change in state of a quantum system. So that's one area where you might see matrices being used. I mean, an example is in Schrödinger's equation. We saw an image of it in the first bit of this video in almost the gold letters, where we had H, and H stands for the Hamiltonian. And if we're writing the state of our system as a vector, then the Hamiltonian is a matrix which causes this vector to change over time. So the Hamiltonian describes the evolution of our quantum state with respect to time. So that's one use of matrices, and that's very important because physics is all about, if we've got the initial conditions, predicting how a system will evolve and change. Now, another use of matrices in quantum mechanics refers to the idea that not only can matrices cause vectors to, say, rotate, they can also squish or stretch a vector. So they don't actually change the orientation of the vector in this case, they just make the vector bigger or smaller. Now, because in quantum mechanics, because it's a probabilistic theorem, the length of a vector actually corresponds to the total probability, and because we are always going to measure a system in a classical state, even if we don't know what one that will be, we always renormalize the vector to have length 1. So the stretching or squishing doesn't actually correspond to a change in the state of the system, because the length of the vector is always renormalized back to 1, so stretching or squishing is actually, in physical terms, altering the state. However, the stretching or squishing refers to introducing a scale factor, which is stretching or squishing the vector, and the scale factor actually, it turns out, represents the value for the physical observable we would measure if we found our quantum system in a particular classical state. And so matrices are also useful for extracting information about what values we might measure for a physical observable, and therefore matrices can be thought of as describing observation, or the role of observation in a quantum experiment. Looking at quantum mechanics. So matrices are very useful even when we've got a system, when we're not considering the system as made up of multiple parts, matrices are very useful for describing measuring that system and that system evolving. However, what happens when we've got two systems and we bring them together? Well, for this we need to think about how we can combine the vector spaces together, because say we've got two coins and we want to consider the system of those two coins together. Well, each coin will have a set of possible vectors that can describe its state. So each coin has its own, if you like, vector space, and we need some mathematical operation that will bring those vector spaces together, and we'll look at a couple of options in the next couple of slides, and then look at which one we do actually pick out of those two to describe building a composite system in quantum mechanics. And then we'll describe that very visually using mugs and tea, and almost the most British version of this mathematical operation I could think of. So we'll be doing that, and then we'll be finishing with a brief mention of entanglement. So I'm going to now introduce the first mathematical operation that can be used to bring vector spaces together, so to combine vector spaces, and this is called the direct sum, and the idea of sum might tell you something about how this operation is going to work. So if we have a vector space, which loosely speaking is a space which has all the properties such that vectors can be meaningfully defined and exist on it, and we can do standard vector algebra, then we can consider mathematically what happens if we bring those vector spaces together. And as a reminder, that's very important for us as physicists, because we would like to talk about composite systems in quantum mechanics, and composite systems will involve bringing vector spaces together. So the direct sum does this by essentially, if we've got two vector spaces, so let's say one vector space has vectors living on the xy plane, and another vector space just corresponds to the z component of a vector. Well, if we add the z component to the xy components, then we end up with a vector with three components, an x, a y, and a z component. And so using the direct sum, we're just kind of stitching dimensions, if you like, together, and the dimensions of the vector space formed by the direct sum will just be the sum of the dimensions of our individual kind of subspaces. So we have an example of the equation for the direct sum here. So the direct sum is kind of about stitching components of a vector together, or using vectors, components of vectors, to build up a larger vector. And this is actually a very useful bit of maths if we're talking about projection operators, where a vector, say, collapses such that one of its components goes away, and it ends up existing solely in one of the subspaces of the overall vector space. So almost the reverse of the direct sum. And so the idea is quite useful there. And projection operators are quite useful if we're thinking about what happens when we measure a quantum system, because when we measure it, this quantum state vector does collapse to a classical state, and we can think of that as mathematically applying a projection operator onto our vector space describing our quantum state such that it turns into a vector living solely in a space with regards to a classical state. So that's where you might think of using the idea of the direct sum. So the direct sum is about stitching dimensions together, but there's another, seemingly less useful, although for our purposes we'll see it will be more useful, way to combine vector spaces together, and that's called the tensor product. And we'll come on to that in the next part of this video. So, for the tensor product, we call it a tensor product because it's actually, as well as a way of stitching vector spaces together, it's a way of taking two tensors and forming a tensor of higher rank. That is a tensor with more indices. Now, for those of you which are not sure what a tensor is, I've done a full 45-minute video, although hopefully it won't seem quite that long, on tensor algebra. But tensors are quite useful in physics, but for our purposes, we can think of a rank 1 tensor as an object with one index, so that'd be a vector, whereas a rank 2 tensor would be an object with two indices, which would be a matrix. So a tensor product can actually take the vector spaces and stitch them together in such a way that when we take the tensor product of two vectors, we will actually end up with a matrix. And the dimension of the space described that we get when we do the tensor product is actually the product of the tensor space, so the product of the dimension of the vector spaces of the subsystems. Because say we've got a vector with two components and we take the tensor product with a vector with two components, we'll end up with a matrix which will have four components, so two square components. And an operation which kind of does this produces a matrix, which we can also think of as a vector living in a vector space with n squared dimension, because we can always just rewrite the components of a matrix as just components in a row. We're free to do this, providing we keep track of the order, the relative order of the components. So a 2 by 2 matrix can always be written as a, vector with four components. So in other words, we're producing, if you like, a vector through the tensor product, which lives in a vector space of n squared dimensions, if we form it by taking the tensor product of vectors that live in an n-dimensional vector space. And the tensor product, though, if we think of it going back as producing a matrix, looks something like this. Now, looking at the tensor product, you might think this looks very much like the outer product between vectors, and indeed it is the same in a sense, although the tensor product has a more specific meaning. So now we've introduced rather abstractly what the tensor and direct product are. The key takeaway is the direct product returns a vector space with the sum of the, which has a dimension equal to the sum of the dimensions of the vector spaces, sub-vector spaces, whereas our product, tensor product, returns a vector space whose dimension is equal to the product of the dimensions of the sub-vector spaces. And we now going to think about, if we've got a composite system, whether we would like to use the direct product or tensor product to build our vector space for describing the state of our composite system. So, as we've said, in quantum mechanics, the state of an individual system is described by a vector, which lives in a particular vector space. And when looking at a composite system, a system made up of individual subsystems, then the total system will have a vector space constructed from the individual vector spaces. So to work out what operation we would like to use to combine these vector spaces, what will be appropriate, whether it be the direct product or whether it be the direct sum or the tensor product, let's think a little about a system, and to keep things simple, we use a classical composite system and how we will construct it from its classical subsystems. So for this, consider we want a mug with a hot drink, and myself coming from Britain, when I think of a hot drink, I think of tea or coffee. There are many other lovely hot drinks out there. Milk with cinnamon, nutmeg, is probably a really good one to try. But tea and coffee are lovely hot drinks. And let's say I have two possible mugs to pick from, a large mug and a small mug. Well, I could ask, okay, I want to describe now a state referring to all possible combinations of these two drinks and these two mugs, such that whatever kind of mug of tea or coffee I have will be represented somewhere, will have a component somewhere in the overall state or object I'm using to describe the state of my composite system. So how many possibilities or how many components will this state need to have? Well, there are two drinks, tea or coffee, and there are two possible mugs, a large mug or a small mug. And therefore, there are in total 4 unique combinations. So my overall state needs to have 4 components for my overall system. So the individual subsystems, the type of mug, and also the choice of drink, there are only 2 options, for each of these. And therefore the subsystems we can think of as vectors with 2 components, whereas the overall system, the composite system, has 4 components. In other words, the dimension of the overall system is the product of the dimension of the subsystems. So we want to use the tensor product, not the direct sum, to produce a state of the overall system when describing the overall system from the individual subsystems. So when we're talking about a composite system in quantum mechanics, we construct it by taking the tensor product of the individual subsystems, and as we've said before, we can think of this as producing a matrix, and so matrices are used to describe the state of composite systems, and we call these matrices in quantum mechanics density matrices. Density because probability density is associated to them due to the probabilistic nature of quantum mechanics, but they're matrices because they're tensor products of vectors. And this has been very wordy, but I would like to show you in picture form a kind of pictorial demonstration of this equation with our mug of our hot drink, to show you how the tensor product works in picture form, because I'm aware that this is a lot of words, and it'd be nice to have a visual demonstration of this mathematical operation. So here we can see visually represented what I was saying. Now, due to taking photos and wanting to keep the images being clearly visible, unfortunately the small mug ended up looking a similar size to the big mug. but the mug with the cherries, slightly with the kind of red ring at the top, that's actually the small mug, and the kind of greenish mug with the handle, well, with the green handle, that's the large mug. So we can see here we've got our subsystems. We've got the possible drinks, tea or coffee, represented by a tea bag, and also a large jar of instant coffee. A jar that is almost critical to life these days to keep everyone awake, because life is constantly active now we have the internet and social media. So a very important drink indeed, and also really good for studying, at least in the short term, though I wouldn't recommend it in the long term. So we have two drinks, tea and coffee, and we have two possible sizes of mug, or at least from the pictures, two different mugs. And the total number of unique combinations is 4. So we've got the small mug with the tea, the large mug with the tea, the large mug with the coffee, and the small mug with the coffee. And that's all possible unique combinations. And so whatever drink I have, given the available mugs and available drinks, whatever drink I end up having, will be represented in the final state somewhere. So the final state, or if you like, the state of the composite system, is given by the tensor product. If we used the direct sum, then the direct sum would, well actually, okay, here the direct sum would work. Because it just so happens that kind of squaring the dimension of the vector space and multiplying the dimension of and adding the dimensions of the vector space result in the same thing, because the vector space is two-dimensional. But if we had the vectors living in three-dimensional space, then the direct sum just wouldn't produce something with enough components to fit all the possibilities. So we need the tensor product. And so now we've talked a little bit about the tensor product, we're going to finish this by wrapping it up by talking about entanglement. So, as we've said, the density matrix is defined to be the tensor product between state vectors in quantum mechanics, and so the state of a composite system is actually described using a matrix. And composite systems have one very peculiar property that they can have that doesn't exist in classical physics, and that's something called entanglement. Now, entanglement is where the subsystems become so entangled, if you like, that one can no longer actually meaningfully talk about the state of an individual part of that subsystem. In a very kind of real way, the subsystems stop being subsystems, and we can only talk about the system as a whole until a measurement occurs which will cause the wave function to collapse using a projection operator mathematically, and that will actually break this entanglement, thus allowing us to talk about the state or the state vectors of the individual subsystems. So that's kind of what entanglement is, and because entanglement corresponds to the idea of a composite system and information found within that composite system, whenever you're talking about entanglement in mathematical detail, you use matrices. So matrices are really useful in quantum mechanics, from talking about evolutions of quantum states to talking about measurements of quantum states, and also to talking about composite systems and things like entanglement, and also related topics like decoherence. So matrices are wonderful, very useful, and very applicable across quantum mechanics, and one really good reason to learn matrix algebra is to do quantum mechanics. So I really hope you've liked this video. I hope you found it lots of fun, and hopefully see you for another video in not too long. And if you like this kind of content, please subscribe or hit the like button. That will allow kind of these videos to be seen by more people, and also will notify you when new videos come. And as ever, if there's a topic you would like me to cover, please comment it down below. And I really hope you have a great day, and hopefully see you for more wonderful physics shortly.